In this video, we are finishing chapter 3, and we have to go over the parts of the brain and then how to look at the brain. So it shouldn't be too long. The first section we're going to talk about is the forebrain. The forebrain is the largest part of the brain, bigger than the midbrain and the hindbrain, and it has the cerebral cortex, which we talked about before, that surface of the brain, and what they call subcortical structures. So we are going to talk about the different lobes that are in the forebrain. There are 4 lobes that you should know. The most important one, I would say, is the frontal lobe. And for these, you need to know what they do, the function of that part, how they're specialized, but you don't, and if they're in the left or right hemisphere, if they're only in part of it. But you don't need to know location beyond that. You're not going to see a picture of the brain on the test and you have to label things. That's too particular. So first, frontal lobe. The frontal lobe does reasoning, motor control, emotions, and language. And the frontal lobe is divided further into the motor cortex, prefrontal cortex, and Broca's area. The motor cortex does movement, coordinates, plans movement. The prefrontal cortex does higher level cognitive things. It is, for example, Phineas Gage, whose name is down there. He was a railroad worker who had a railroad spike shot through his head by accident, and it damaged his frontal lobe, especially that prefrontal cortex, and it changed his personality some. Now, a lot of the reports about this exaggerate a little bit. It wasn't that huge of a change, but he became less reliable, became more rowdy, because that prefrontal cortex does judgment, does planning. And so what I want to do is show you a video of a Vietnam vet who had damage to the frontal lobe, especially that prefrontal cortex. And you can see for him how that affected how he acted. So watch that video now. And final thing for the frontal lobe is Broca's area. Broca's area is in the frontal lobe. It's only in the left frontal lobe. So this is one you would need to know. Just the left hemisphere of the frontal lobe has Broca's area. And this is in charge of language production. So when you produce speech, when you know what to say, also when you know what to write, because that's still speech, even if it's written. And so if Broca's area is damaged, if you have what they call Broca's aphasia, then you will have difficulty speaking. Your words will come out jumbled. It will be hard for you to find the words to say, potentially. For example, Gabby Giffords, the congresswoman who was shot in the head, her Broca's area is damaged. And if you see a video of her giving a speech now, it's very halting, it's very simple words, because that Broca's area wasn't able to fully repair itself. So that is frontal lobe. The parietal lobe is in charge of processing information from your body's senses. So, for example, in the parietal lobe, you have the the somatosensory cortex, and that is in charge of processing sensory information from across the body. Things like temperature, touch, all of that sort of stuff. That's parietal lobe. The temporal lobe is associated with hearing, memory, emotion, and some parts of language. Specifically in the temporal lobe, you have Wernicke's area. Also, just in the, or actually Wernicke's area, it's German, W pronounced like a V. In Wernicke's area, it's in the left hemisphere, and it is in charge of speech comprehension. So understanding what other people say to you. If you have Wernicke's aphasia, when people speak to you, it's going to sound jumbled. You're not going to be able to understand what they're saying to you. And generally in the temporal lobe, you have the auditory cortex as well that processes auditory information. So that is the temporal lobe. And then finally, the fourth lobe is the occipital lobe. The occipital lobe is in charge of vision. And so, yeah, it's the primary visual cortex. And that is it for the lobes. Final thing on this slide, another part of the forebrain is the thalamus. And the thalamus is in charge of sensory relay for the brain. So having sensory information go from other parts of the brain to the parts where it's going to get processed. So all senses except for smell are routed through the thalamus before they go to the other parts. Smell is different. Smell goes to the limbic system, straight to the limbic system. The limbic system in general is involved in processing emotion and memory. And if you think about it, and smell, if you think about it, smells are often connected to emotions, smells are often connected to memories. You smell a certain cologne and it reminds you that your grandpa wore the same thing. And so that's why smell goes to the limbic system instead of the thalamus. Some subcomponents for the limbic system that you should know, the hippocampus. The hippocampus is in charge of learning and memory. And for the hippocampus, it's the relay station where memories that you want to store long-term are kept until they're moved to their permanent long-term location. And so that transition to the long-term location happens when you sleep. And actually, I'm going to talk about HM. HM was a man who, I think he was having seizures. For some reason, he had to have his hippocampus destroyed. And so again, your hippocampus, where things are stored before they move to long-term memory. And when we talk in the memory chapter, this will make a little more sense. But if you don't have a hippocampus, or if your hippocampus is damaged, you can't create new long-term memories. And so for HM, he would forget everything after a few minutes. He could have short-term memory, he could remember something for a short amount of time, but he couldn't create any new long-term memories. So he couldn't, if you were talking to him and then he turned away for a couple of minutes and looked back, he would have forgotten that you would come into the room. He would have forgotten what your conversation was about. No new memories could be created, no new long-term memories could be created because that hippocampus was damaged. Another part of the limbic system is the amygdala, which is in charge of strong emotions and connecting emotions to memories, especially strong emotions like fear. Your amygdala is in charge of fear. And then the hypothalamus is in charge of homeostatic processes. And that's things like regulating your body temperature, your appetite, your blood pressure. If your hypothalamus is damaged, potentially you don't have an appetite anymore. Potentially you're always hungry. Things like that. So that is it for the limbic system. That's it for the forebrain. For the midbrain, these are the structures that are deep inside your brain, between the forebrain and the hindbrain. And you only need to know one part of the midbrain, the reticular formation. That is important for regulating your sleep-wake cycle, your arousal and alertness, People who have ADHD have smaller reticular formations, and so it's harder to be alert. It's harder to pay attention because that part of your brain isn't as big as it should be. And then finally, hindbrain. Your hindbrain is at the back of your head. It includes the medulla, the pons, and the cerebellum. And part of the brainstem. The brainstem, let me go over brainstem first. The brainstem involves the medulla and the pons, as well as the midbrain. So the brainstem is bigger than just the hindbrain. Medulla, pons, midbrain, all in the brainstem. The medulla is in charge of automatic processes of the autonomic nervous system. So this is going to be things like breathing, heart rate, blood pressure. That's the medulla. Your pons is in charge of regulating brain activity while you are asleep. So how your brain is active while you're asleep, it's going to be connecting that brain and spinal cord as well. And then finally, the cerebellum. The cerebellum receives information from your muscles, your tendons, your joints, and your inner ear, and helps to coordinate balance, coordination, movement, motor skills. It also is in charge of, or plays a part in processing memories connected to movement, what we call procedural memories. You'll learn more about that in the memory chapter. But if you know how to ride a bike, your cerebellum plays a part in that memory because it's a memory connected to a skill of movement. So those are the parts of the brain you need to know. Final thing to go over is ways to look at the brain. There are a few ways you need to know. First way you can look at the brain is a CT scan, CAT scan. Fancy name is computerized tomography. What this is that it takes a bunch of x-rays and then puts them together so that you can get a 3D image of that part of your brain. The good part about this is that it can show you structures and if there's potential damage. For example, in the video of the vet with the damage you saw, a CT scan, it can look for shrapnel, tumors, that sort of thing. Couple of downsides, it doesn't show you activity in the brain, and it's x-rays, radiation, so you can't have a bunch of them. You can also have a PET scan, positron emission tomography, and these are a PET scan. They inject you with a radioactive isotope, like radioactive sugar, and then they see where that sugar goes in your brain. They can see it because it's radioactive. And the idea is wherever that sugar goes, that's the active part of your brain because it needed the energy. And so it looks at activity, not just structure, because it looks at what parts are active. And so in this case, it's a PET scan for someone with Alzheimer's versus someone without, less activity in the patient with Alzheimer's. Also, you cannot have a bunch of PET scans because it's radioactive sugar. It's radiation. Next thing is MRIs, magnetic resonance imaging. What this is they stick you inside a huge magnet and they pulse it. And the hydrogen atoms in your bodies move. They have a charge. And so they vibrate when this magnet pulses, and it basically measures how long it takes for that vibration to stop, and and they look for that sort of electromagnetic signal that it's releasing as it stops vibrating, and it can interpret that to tell density of substances. So it looks at structure, not activity. It's just a snapshot of your brain, or not just your brain. You can get an MRI on other parts of your body. But what makes it differ from CT scans is that, one, there's no radiation, so it's a little safer, as long as you don't have metal in that part of your body. And two, it can look at soft tissues in a way that CAT scans can't. So it looks at soft tissue structures in this case in your brain. But again, no activity. If you want to look at activity, then you can look at a functional MRI. fMRI is basically, they take a bunch of MRIs one right after the other, and it's kind of like, you know those books where you flip through it and you can like MRI versus an fMRI. It's multiple MRIs in a row, and so by moving them you can see change in structure. The assumption being that the changes are due to activity because it's due to blood flow and oxygen levels in that part of the brain. So an fMRI tells you activity, whereas an MRI just tells you about the structure. And then finally, you have an EEG, an electroencephalogram. Electroencephalography is looking at brain activity on the surface of the brain. So it's only looking at the surface of the brain. It can't tell you specifics. It can't say there's brain activity in the amygdala or the reticular formation. It just says, here are the types of brain waves you have. It's very non-invasive. You just put electrodes on your scalp and it can register it. You use this a lot to tell, like, if someone's having a seizure. You use this to tell what stage of sleep somebody is in. Those are two of the big reasons you would use an EEG. But that is it for how to look at the brain, and that is it for this chapter.